In this unit, we will be discussing integration by substitution. There are two types of integration by substitution. The first one is by algebraic substitution, and the second is by trigonometric substitution. Before we discuss examples of integration by substitution, let me give you the integrals of inverse trigonometric function. The integral of du all over the square root of a squared minus u squared is equivalent to the arc sine of u over a plus c. The integral of du all over a squared plus u squared is equal to 1 over a arctangent of u all over a plus c. And the third one, the integral of du all over u times the square root of u squared minus a squared is equal to 1 over a arcsecant of the absolute value of u all over a plus c. And always take note, in using integration formulas, du is always the exact differential of u, where u is the variable of integration. There are some functions that involve radicals or fractional powers of x. For these types of functions, the integrand can be simplified by algebraic substitution. Let us illustrate that. If we want to evaluate the integral of the square root of x dx divided by 1 plus the cube root of x, we could write the integral in terms of fractional exponents. So we could write this as the integral of x raised to 1/2 dx all over 1 plus x raised to 1/3. Now, since we have a fractional exponent, x raised to 1/2 and x raised to 1/3, it would be nice to consider the least common denominator of 1/2 and 1/3, which is 6. So we make use of a substitution wherein we let x be equivalent to z raised to 6. Z is the introduced variable for substitution, and 6 is the least common denominator of 1/2 and 1/3, which are the exponents of x in the integrand. And if we take the differential of x, then the differential of z raised to 6 now becomes 6z raised to 5 dz. And at the same time, x raised to 1 over 6 is actually equal to z. We then use these substitutions for the original function. The integral of x raised to 1/2 all over 1 plus x raised to 1/3 dx, if we substitute the value of x raised to 1/2, this will become the integral of x raised to 1/2 becomes z raised to 6, and the whole quantity will be raised to 1/2. Since x is equal to z raised to 6, and in the original equation, x is raised to 1/2. For the denominator, it follows, since we have an x raised to 1/3 in the denominator, and our x is equal to z raised to 6, and originally our x is raised to 1/3, so we have to raise z raised to 6 also to 1/3. So our final integral, it becomes the integral of z raised to 6 raised to 1/2 all over 1 plus z raised to 6 raised to 1/3 times dx. And what is dx? dx is 6z raised to 5 dz. If we simplify this, this becomes the integral of the numerator becomes z cubed, because 6 times 1/2 is 3. And we copy the new differential of x, which is 6z raised to 5 times dz. For the denominator, we could simplify that as 1 plus z squared. And simplifying further, this becomes the integral of z raised to 8 dz all over 1 plus z squared, and then we multiply that by 6 before the integral sign. Take note that the first rule of integrating a rational fraction in the integrand is to be sure that the degree of the numerator must be less than the degree of the denominator before applying any integration formulas into the integrand. Otherwise, we have to do long division. In the case of our integral, the rational fraction is actually having a degree of the numerator that is greater than the degree of the denominator, making this an improper fraction. So we have to divide the numerator by the denominator, and we could use long division. Dividing, we could take the quotient, which is z raised to 6 minus z raised to 4 plus z squared minus 1 plus 1 all over z squared plus 1. With the new quotient that we have, we will substitute this as the new value of the rational fraction from the integrand. So it becomes the 6 times the integral of the quantity z raised to 6 minus z raised to 4 plus z squared minus 1 plus 1 all over z squared plus 1, multiply it by dz. If you notice, the first, the second, and the third term, which are z raised to 6, z raised to 4, and z squared respectively, could be integrated by the use of the general power formula. The fourth term could be integrated just by using the first property of integrals, and the fifth term or the last term can be integrated by applying the formula of the integrals of inverse trigonometric function. Integrating, we get here 6 times the quantity z raised to 7 all over 7 minus z raised to 5 all over 5 plus z cubed all over 3 minus z plus the arc tangent of z plus c. Take note, originally, we made a substitution, or we introduced a variable which is z that is actually equivalent to x raised to 6. Now, we will bring back the original value of z, which is x raised to 1 over 6. So, replacing z with x raised to 1 over 6, we obtain our final answer to be 6 over 7 x raised to 7 over 6 minus 6 over 5 times x raised to 5 over 6 plus 2 times x raised to 1 half minus 6 times x raised to 1 over 6 plus 6 times the arc tangent of x raised to 1 over 6 plus c. Let us evaluate the integral of x raised to 5 times the square root of the quantity x squared plus 4 dx. First, we let z be the entire radical, which is the square root of the quantity x squared plus 4. And if we square both sides, z squared will be equivalent to x squared plus 4. The next step is to solve for x squared. X squared becomes z squared minus 4. And if we take the differential of both sides, we get 2x dx is equivalent to 2z dz. And simplifying, we get x dx is equal to z dz, or dx is equivalent to z dz all over x. The first thing to be done is to fix the terms of the function, and then after that, we now can make the necessary substitutions. The integral of x raised to 5 times the square root of x squared plus 4 dx could be rewritten as the integral of x raised to 4 times the square root of x squared plus 4 x dx. Further, we could write this again as the integral of the quantity x squared times the square root of x squared plus 4 dx. And if we start to substitute the values, x squared is equal to z squared minus 4, z is equal to the square root of x squared plus 4, and x dx is equal to z dz into the equation, then we could take the integral of the quantity z squared minus 4 times z times the quantity z dz. If we expand this, we get the integral of the quantity z raised to 6 minus 8z raised to 4 plus 16z squared dz. We now can integrate each of the terms of the integrand using the general power formula. Integrating, we get z raised to 7 all over 7 minus 8z raised to 5 all over 5 plus 16z cubed over 3 plus c. We now can return all the x variables from the substitutions. If we return the value of x from the integral that we just derived in terms of z, we get this final answer. Let us evaluate the integral of dx all over x times the square root of 4x minus 1. We let the entire radical be equivalent to z. Z will be equivalent to the square root of 4x minus 1. If we square both sides and solve for the value of x, we get z squared is equal to 4x minus 1, wherein x becomes equivalent to z squared plus 1 all over 4. If we differentiate both sides and solve for dx, we get 2z dz is equal to 4 dx. Solving for dx, we get z dz all over 2. Substituting into the integrand, the integral of dx all over x times the square root of 4x minus 1 becomes the integral of z dz all over 2 all over z squared plus 1 over 4 times z. If we simplify this, it becomes the integral of 2 dz all over z squared plus 1. This could be integrated by using the formula of integrating inverse trigo functions. We can get an answer of 2 arctangent of z plus c. Take note that z was actually equivalent to the square root of 4x minus 1. So if we substitute the value of z in terms of x, our final answer is 2 times the arctangent of the square root of 4x minus 1 plus the arbitrary constant c.